first of all, the unit starts out with characterizing numbers, and all numbers can be categorized into divided into two groups. We have our real numbers, which are all of these over here in the light blue, and then we have something called imaginary numbers, which are another group of numbers. So if you think of all the numbers that we know, they can be divided into two groups: real numbers and imaginary numbers. And please feel free to ask questions. If any come up, you can use the chat window or grab your mic. Both work great. Let's look at the imaginary numbers first and get those out of the way. We are going to be looking at imaginary numbers in more in depth later on in the course, but I'm just going to introduce them here right now. I'm going to grab my pen. There we go. So if you think about the square root of 9, the square root of 9, when you want to think about any square root, you're trying to think of a number when multiplied by itself is equal to the number underneath the square root sign. So the number when multiplied by itself that equals 9 is going to be 3. And that's because 3 times 3 is equal to 9. Another thing that you can think of is that negative 3 is also the square root of 9, because negative 3 multiplied by itself is equal to 9. When you multiply two negatives together, my pen doesn't want to work with this. When you multiply two negatives together, you get a positive number. So that's where that comes from. So when you have the square root of 9, you either have a negative 3 or a positive 3 as your answer. If I were then to say, okay, let's think of the square root of a negative number, negative 9. Well, we already know that positive 3 times positive 3 is equal to positive 9, and negative 3 times negative 3 is also equal to positive 9. Therefore, we don't really have a solution for two numbers when multiplied together that give us a negative number. And that's where imaginary numbers come in, because even though there isn't a number that when you multiply together is going to give you a negative, there is a symbol that we can use for that. So what we say is that if you have the square root of a negative number, negative 1, we're going to call that an imaginary number, and we're going to give that a special symbol. We're going to give that the symbol of I. There we go. So an imaginary number can be shown as the symbol I. And an imaginary number is something that we're going to use later on in the course, and it helps us to simplify answers that involve imaginary numbers. So that's all you need to know for now, is that anytime you have the square root of negative 1, this gives you the imaginary number. Okay. What we're really dealing with in P.1 are all the other numbers that aren't imaginary. These are the real numbers. And real numbers can be divided into subgroups. And the subgroups that we have for our real numbers, first of all, are our rational numbers, which are all here, which include integers, whole numbers, and natural numbers. And then our irrational numbers. So you can picture that all of the numbers that we know can be divided into two groups: real numbers and imaginary numbers. And then real numbers are divided into two groups. Those are our rational numbers and our irrational numbers. And then rational numbers are divided into subgroups as well. So we're going from big groups down to little groups. Let's look at our irrational numbers first. So our irrational numbers are numbers that can't be represented by a fraction that has a whole number on the top and a whole number on the bottom. So a numerator needs to be a numerator that's whole, and our denominator has to be whole too. And just to remind everybody, the top number in a fraction is called the numerator, and the bottom number is called the denominator. And in order to be a fraction, both of these have to be a whole number and not a decimal number. And irrational numbers cannot be expressed as fractions. And the reason for that is that when you look at their decimal equivalent, so for instance, if we look at the square root of -3, and we put that into our calculators, sorry, the square root of negative square root 3, we don't get an exact number, and that's what these squiggly lines are. What we get is we get a decimal, and the decimal looks like this: 1.73205, and it keeps on going without any repeats. So that's supposed to be 3 dots there. And it will go on forever, and whenever you have a number that can't be represented as a fraction, and the decimal doesn't repeat and doesn't end, then that's going to be an irrational number. Square root of 2 is another example. The decimal equivalent of square root of 2 can only be approximated because, again, it's 1.414214 ... It doesn't end and it doesn't repeat. Pi is a famous example of irrational numbers. So pi, which is shown as this symbol here, it goes on forever as well. It's approximately equal to 3.14 and then keeps on going without any repeats. Not all square roots are irrational though, so don't assume just because the examples here are square roots that all square roots are irrational numbers. So for instance, the square root of 25 is equal to 5. That's a whole number, and that's a rational number. So the square root of 25 is an example of a rational number, and it can be classified also as a whole number because it's equal to 5. So just be careful of that, because some students see that the examples are usually given as a square root, and so they think that all square roots are irrational numbers, but not all are. Folks, give me one moment. The pen's not working the greatest in this slideshow, so instead I'm going to bring up PowerPoint in the background and then share my desktop, and I think that will work better for us. So if you need to pop out and get a drink of water, do that. It's going to just take me 1 minute and I'll be right back up. Okay, I've got it up here. A little bit bigger. I'm going to try and make it. Can everybody see that okay? Whoops. I want to still be able to see my chat function there. Can everybody hear me still okay? Give me a thumbs up or say, let me know if you can see the new slide and if you can hear me okay. Pens, there we go. Awesome. Okay, I should be able to draw on this a little bit better. Sorry about that. Again, we're using Skype for the first time this term, so I'm still working out the glitches, but I think I've got my pen so it will work okay now, and hopefully it's not too small. I can make this as big as there we go. There, that's pretty big. Okay. So we went over the imaginary numbers, we've looked at our irrational numbers and found that it's any number that can't be represented as a fraction and whose decimal it doesn't repeat and doesn't terminate. So now we're going to look at everything else under real numbers. So real numbers, irrational numbers are real numbers, and so are rational numbers. But our rational numbers can all be expressed as a fraction. And then our rational numbers include the subsets of integers, which are our positive and our negative numbers, our whole numbers, which are all of our positive numbers, including 0, and then our natural numbers. And usually we start at natural numbers first and then go up to whole numbers, then integers, and all of those make up rational numbers. Our natural numbers are numbers that are positive but don't include 0, and we call them our counting numbers, numbers that we can count with. So our natural numbers don't include 0 and are all positive. Our whole numbers are all of our positive numbers, but including 0. Integers are now our natural numbers, our whole numbers, and our negative numbers, all inclusive. And then our rational numbers now include our fractions and our decimals. So when you have a fraction or a number such as we said before, the square root of 25 is 5. Those are all rational numbers. You just have to make sure that if it is a decimal number, that it repeats. So for instance, if you had a number like this, and 356 is repeating and it repeats forever, then that is an example of a rational number. So as long as the decimal repeats or has an end, then you know that you have a rational number. And in the textbook and in my math lab, this is the type of question that you might get. You might get a set of numbers, and then you have to go through and categorize each of the set. So this is how you can do that. So I like to start off with the real numbers down here. And if you look up here, real numbers are all the numbers that we know without the imaginary numbers. And you can see that I don't have any of the symbol I numbers or square root of -9 or a square root of any type of negative number. So there aren't any imaginary numbers in this list. So I'm going to say all the above for the real numbers. As long as you're not including an imaginary number, you're okay. Okay, let's look back up and let's start with natural numbers. Looking at this list, can you see any numbers that would be considered a natural number? Remember, your natural numbers are your counting numbers. So 0 is not included as a natural number, and they have to be positive numbers that aren't expressed as a decimal. So looking at this group, 9 is a negative number, so that's not going to work. -4, 5, that's a negative number. 0 is not included as a natural number. Decimals are not natural numbers. Square root of 3 is not, because it's going to be a decimal. 9.2, decimal. How about the square root of 100? Square root of 100 is going to be 10. And 10 is a natural number, so that is going to be considered a natural number. Even though it's expressed as a square root, if you simplify it, calculate it, and find out that the number, what it's equal to, and that number is a natural number, then square root of 100 is going to be a natural number. So Jacob, you've got it. The square root of 100 is going to be considered a natural number. So make sure that if you have anything, understood, if you have anything that you're unsure of, you can always put it in the calculator and simplify to see if it follows. So looking at B, whole numbers are going to be your natural numbers, so you can include your square root of 100 again, but it's also going to include zeros, and you can see that we do have a 0 here. So a 0 is also considered a whole number. It's not considered a natural number, but it is considered a whole number. So square root of 100 and 0, both are going to be whole numbers. Then we're going to build on that. Our integers are going to be, again, our square root of 100 is an integer. It's positive 10, which is an integer. 0 is considered an integer as well, but now we're going to include any negative numbers. So negative 9 is going to be an integer. Negative 4/5 is a fraction, and fractions are not included in integers. We're going to include those in our rational numbers coming up. So looking across here, I don't have any other integers, so that finishes that category. And now we're moving on up to rational numbers. So rational numbers are going to include everything below it. So square root of 100 again, 0, negative 9, but now it's going to include anything that is a fraction. So negative 4/5 is going to be included in the rational numbers. 0.25, it's a decimal, which is a rational number. It's terminating, which means it has an endpoint. It doesn't go on forever. So that's an indication that it's also a rational number. And also, we can rewrite this as 1/4, which is a fraction. So that tells us that 0.25 is also a rational number. So the test you can do to rational numbers is, 1, can you express it as a fraction with a whole number on top and a whole number on bottom? And if you can, then that decimal is a rational number. Or if the decimal is terminating, which is what's happening in this case with 0.25, then that gives us an idea that it's rational as well. Or if you have a repeating decimal, then that would also give us an idea that it is a rational number. Another rational number that we have here is 9.2. And again, it has a terminating decimal, so that's going to tell us that it's a rational number. And if I were to express it as a fraction, I could express it as 92/100. So that's going to also tell me that that's a rational number. Nathan is typing, so I'm going to wait for Nathan's. No problem, Nathan. I'm recording, so you can come back and look at this. It's going to be posted in the news feed probably about 10 minutes after I'm done. Thanks for coming in. And then the last one, the irrational numbers, there's only one irrational number here, and that's the square root of 3. Now you might not know that to look at it, but if you were to put square root of 3 into your calculator, because we know not all square roots are irrational. Some square roots are rational numbers because they can be expressed as a fraction. But if you were to put square root of 3 into your calculator, you would notice that it takes up your whole display screen. And depending on how precise your calculator is, if it takes up the whole screen, that means that it's non-terminating. It's also not repeating. None of the numbers that are showing up are repeating. And so that's those two tests right there, the fact that it doesn't end and it's not repeating, tells me that that's an irrational number. And Tiffany, that's a great question. How do you turn decimals into fractions? So it depends on how many decimals are after, or how many decimal places are after the decimal. So I'm just going to put up a couple of examples here. Okay, if you have just one decimal and you want to put that into a fraction form, remember, you have to remember your place values. So right after the decimal, that place value is our tenths. So that means when you want to change 0.2 to a fraction, you're going to put that number over 10. So 0.2 becomes 2 over 10. Which you can reduce to 1 over 5, but at least it gives you a starting point for a fraction. Does that sound okay for that one, Tiffany? So if you have one decimal place, you're going to put that number over 10. If you have two decimal places, we're now looking at the hundredths. And hundredths mean that you're going to take those two numbers and put it over 100. And if you have three numbers, you now have the thousandth place. And so that means you're going to put that number over 1,000. And then, of course, you're going to want to reduce. But that's a whole different thing. But that's how one of the things that you can do to a decimal. And that's why if you have a decimal that is non-terminating and it goes on forever, come on back, pen. There we go. Oh, no. Sorry about that, I just lost my pen. Doo-doo. Tiffany, let me know if that's okay for you. Come on, pen. Just unplugging my pen and see if it'll come back. Ah, good. Here it is. There we go. Whoop. Okay, so if you have a number that keeps on going, you can't put that into a fraction because you're going to have a numerator that goes into infinity, so that's not going to work. Okay, so that's how you do those types of questions. You want to just start off with natural numbers and work away through each of the categories until you have them all figured out, and going through those tricks that I told you about how you can tell the difference between a rational number and a rational number too helps as well. Before we get into intervals and set builder notation, does anybody have any last questions about the set of real numbers? There's a lot of pressure on you too, Jacob and Tiffany, because you're still left in, but please don't feel you have to stay. But if you have questions, just let me know. The questions are great. Okay, if you guys are good, let's move on to intervals and set builder notation. Tiffany's good on this end. Fantastic. And Tiffany, I saw your email, so if you want to stay after, I can answer any of your questions that you have after, but I'll also respond to your email as well. Since I have you here, I might as well let you know. So let's look at intervals and set builder notation. So that's where we're going next with P.1. We're looking at sets of numbers shown in a number line. And a couple of things about that is that the difference between having parentheses and having a square bracket. Parentheses means that the number is not included in the set, whereas a square bracket means that the number is included in a set. And there's two ways that you can display a set. One is called an interval notation. And the other one is called set builder notation. And you need to know both ways of writing down intervals. So I'm going to explain the difference here in a second. So interval notation, if we look at, this is example A, example B, and example C. If we look at example A, interval notation is probably the easier way to write it down. We're going to look at the starting point here, which is at -1, and we see that we have a round bracket, which means that the set goes up to -1 but doesn't include -1. And then that's our minimum point. And then our maximum point for this set is 4, but that is included. So when you have interval notation, you're going to use round and square brackets to show whether a number is included or not. With set builder notation, it's a little bit different way of writing it. First of all, you're going to use the squiggly bracket, parentheses, and then you're going to use the unknown variable x. And what that means is that x is a number that's what that means. X is a number that, and then there's a line, and that line means is a member of, or such that. So x such that our minimum, that x is going to be between -1 and then x is going to be greater than -1 but less than and equal to 4, and then we finish with the squiggly parentheses. So set builder notation doesn't use the square or round brackets, but you're going to need to use inequality symbols, so greater, less than, and equal to, and you are going to use an unknown variable. So a little bit different in how you write it down, but both ways are saying the same thing. Let's look at B. Looking at B, you see our minimum is around 2.5 right here, or at 2.5, and our maximum is 4. And you can see that the square brackets means that we're going to include both 2.5 and 4 in the set. So in interval notation, it's going to be 2.5 as our minimum, and 4 is our maximum, and then square bracket. And it's going to be any number between 2.5 and 4. All the numbers between 2.5 and 4 are included in the set. So don't think that in interval notation we're just talking about 2.5 and 4. It's all the numbers in between here as well. And then for set builder notation, you just have to make sure you have all the elements. You're going to start off with your curly parentheses. You're going to use x to represent your number, such that, that's what this line indicates. And then we're going to start off with our minimum, 2.5. So x is going to be greater than and equal to this time, because of that square bracket tells us that. So x is going to be greater than and equal to 2.5 and less than and equal to 4. And then we finish it off with a curly bracket. And then our last one, our minimum is -4 and it's not included, hence the curly bracket. And then our maximum, you can see that this time we have an arrow, so that means that our set goes on forever. It starts at -4 and then it goes on to infinity. So we're going to use the infinity symbol here, and whenever you have an infinity symbol you always have to close with a round bracket. Never use a square bracket with infinity symbols. So with infinity, always use the round brackets, okay? And then to express that, x such that, whoops, we're going to use negative 4, greater than equal to that. And then, actually with this, because we're infinity, we're just going to say that x is greater than 4, not equal to, because it is a round bracket. So we don't use an infinity symbol in the set builder notation. We're just going to write it with the inequality symbols. So x is going to be greater than negative 4, and that tells us that it will go on to infinity that way. Jacob, Tiffany, how does that sound? Give me a thumbs up if you're okay, or let me know if you have any questions. I always like to pause just in case. Okay, awesome. Love the thumbs up. Okay. Once you know how to write sets of numbers using interval notation and set builder notation, the next thing is to be able to solve for intersections and unions. So the first thing we're going to look at is unions of sets, and the next thing we're going to look at is intersections. And intersections and unions have symbols. So if you have an intersection of sets, that's going to be your upside down U. And if you're looking for the union of sets, then you're looking for the right side up U. And you can use graphs in order to solve intersections and unions of sets, but you're going to express the answer in either interval notation or in set builder notation. So first of all, we're looking at the union of 1 to 4 and the union of 2 to 8. So how you do that is you're going to draw each of these sets. So I'm going to draw this set first, which is going to be 1 is my minimum and 4 is my maximum. And I'm using round brackets because that's what they used in when they wrote the set. So this was a round bracket. So that means that everything in here is going to be included. And then looking at the next one, whoops, how did I lose that? There we go. Looking at the, okay, and then looking at the next one, it's going to be a minimum of 2, but it's included this time, so I have my square bracket, and a maximum of 8, and again that's included, so I'm looking at everything in here. Now to solve for that, what I'm going to do is I'm going to take what my first set includes, which is my minimum of 1, and that goes to 4, like that. So that's all part of the union. And then looking at my second set, it's my 2, and it's going to go all the way to 8. So I know that my solution set is going to at least include all of those things. But what I have to make sure is I get my brackets right. Because the 1 is not included in the set, I'm going to put a round bracket here, and that is copied from there, but my 8 comes from that second set. So that's going to be a square bracket just like it is here. And that means that my set then in interval notation is going to be between 1 and 8 and include 8 but not include 1. So that's how you do it by the graph. So a union is going to include all the numbers that are in both sets, but you have to be careful of whether the minimums and the maximums are included or not. And in this case, our minimum is not included because it wasn't included in the first set, but my maximum is included because it was included in this part here. And then if I wanted to write that in set builder notation, I'd use curly brackets. X is a member of the set where I have x is greater than 1 and less than and equal to 8. So that's the solution set for the union of set 1 to 4 and 2 to 8. Let's look at another example. This time we're looking for the intersection, as we can tell by the symbol here, and we're looking at the set 1 to 4, whoop, and with round brackets, and 2 to 8. So in this sense, now what we're doing is we want to just include the numbers that are that are shared by both sets. So when we're looking at sharing both sets, we're looking at starting at 2 and then ending at 4, because those are the only numbers that both of the sets share. So when you're looking at this now, you can see that 2 is included, so we're going to use the square bracket with the 2, and the 4 isn't included in the first set, so that means we have to use a round bracket in our solution set as well. So our solution is going to be square bracket 2 and round bracket 4, because the 2 is included in both sets, but the 4 is only included in the second set but not the first set. So that's why you have a round bracket with the interval notation. And then if you were to write it in set builder notation, you would have that x is greater than and equal to 2 and just less than 4, because it can't be less than and equal to, because 4 is not included in that intersection. So intersections are numbers that are shared only by both sets, whereas the union is all of the numbers included in both sets. Can you see the difference between that, guys? Is that okay? Tiffany's good on that one. Great. Okay, so that leaves us with absolute value. So absolute value is sort of what we end P.1 on. And absolute value is the distance between 0 and a number on the number line. And it doesn't, oops, back here. So if you have a number line, as so, absolute value tells us the distance any number is from 0, and it doesn't matter whether a number is negative, so 1, 2, let's do -3, or let's say +2. It's looking at the distance between that number and 0, and it's always represented as a positive number. So -3 is 1, 2, 3 steps away from 0. So the absolute value of -3 is the distance. -3 is away from 0. So the absolute value of -3 is going to be +3, because it's 3 steps away from 0. 2, if we wanted to know the absolute value of 2, again, it's the distance away from 0, which is 2 steps, so it's going to be 2. The answers to absolute value questions are always going to be positive, because it's always the distance that something is away from the 0. So if you're looking at even really big numbers like -10.65, and using the absolute value bars, that's what these mean. So the bars tell us what is the absolute value of -10.65. Well, -10.65 is a distance of 10.65 away from 0. So it's always going to be a positive number. Where it can get tricky is if you're dealing with symbols like pi. If you're looking for the absolute value of pi, pi is the equivalent of 3.14. So you can just leave it as pi, or you can, say the approximate value, which is 3.14, repeating, or not repeating, non-terminating. So you could write it like that. If you have negative pi and you want to know the absolute value of that, negative pi is going to be somewhere around, a little bit closer, but maybe around here. That would be negative pi. Well, negative pi is 3.14 steps away from 0, or pi away from 0. So you're just going to express that as positive pi. So you can also do the absolute value of symbols as well. Just remember, we're always looking at the distance that representation is away from 0. So let's see this in action. It says find the distance between -4 and 5 on the real number line. So one of the real-life example of this is what would be the change in temperature on a day when you start out the day with -4 degrees Celsius in the morning, and by the afternoon it's now going to be +5. Very, very Nova Scotia-like temperatures. So what we're looking at is we're looking at the distance that these 2 points are from each other. So we could always count on our number line how many steps between them they are, but we also can set it up this way. We can say that to look at the distance, we can use the formula of the absolute value of A subtract B, where A is equal to -4 and B is equal to +5. Or we can say B minus A absolute value for this distance as well. So either one of these formulas are going to work. I'm going to show you using this one right here. So if A is equal to -4, which is our first number, and B is equal to +5, which is our second number, I'm going to plug that in. A is equal to -4, subtract +5, and then find the absolute value of that. So I'm going to simplify inside. I'm going to say -4 subtract +5 gives me -9. And then the absolute value of -9 is always going to be its positive form, which is going to be +9. And just to show you that the other formula works as well, the absolute value of B minus A, so that's going to be 5 minus -4, absolute value, and 5 subtract -4 is the same as adding, so I'll get +9, and the absolute value of +9 is 9. So you can see that either using the first formula or the second formula, I'm still going to get my answer to be 9. And if I went back to my my number line, you can see that I do have 9 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9 steps on my number line. When you're doing these types of problems, you don't always want to draw out a number line. It's kind of the idea that you don't always want to add and subtract using your fingers, because sometimes you're not going to have enough fingers to add and subtract. So it's good to always have a method outside of using a number line or using your fingers, and that's why we use this formula. Let's look at bigger numbers where you wouldn't want to perhaps draw out a big number line. Let's say that we wanted to, I'm going to give us another example down here, example 2. Let's use some bigger numbers, and this time say, let's look at -526, the distance between -526 and +60. Let's find the distance of those numbers, because I don't know about you, but I wouldn't want to draw a number line starting at -526 and all the way to 60. That would be a pain in the neck. So what I'm going to do is I'm going to assign A as -526 and B as 60, and I'm going to use the formula of A subtract B in absolute values to find the distance. And that's going to give me the absolute value of -526 subtract +60. And then I'm going to simplify that. So I'm going to say -526 subtract +60 is going to give me -586. and then I'm going to get rid of my absolute value signs, and negative 586, the absolute value of that is going to be 586. So that means that the distance between those two numbers is 586. Jacob, Tiffany, does that make sense on why we use the formula and how we use the formula? You can either use A minus B absolute value or the absolute value of B minus A. Just be careful of your signs when you do that. Great. Kind of fun. Good. Tiffany, I think what you mean is that you understand it now, and then hopefully in practice you'll be able to understand it as well too. If you find that when you're practicing these and you hit one that gives you a problem, just post to the Q&A, because I'm sure if you struggle with that question, you're going to have other classmates that do as well. I think where students find that they have problems is when you add in numbers that are a little bit more complex, like square roots or symbols. So I'm going to give you an example of how to do that. So first of all, when you're given an expression like the absolute value of 1 subtract the square root of 2, the first thing that you want to do is look at what the equivalent number is inside the bars. So all I'm going to do is I'm going to take 1 subtract square root of 2, and I'm going to find the decimal equivalent for that. I'm going to put that into my calculator. I'm going to say 1 subtract the square root of 2, and I see that that is approximately equal to negative 0.414. Then what I'm going to do is, looking at this, I'm going to see, is that greater than or less than 0? And I know that because it's negative, that means it's going to be less than 0. If the number is less than 0, when you take away the absolute value bars, what you're going to do is you're going to flip the terms. So to show that, to evaluate the absolute value of that number, because it is less than 0, when I rewrite it, I'm going to flip the terms. I'm going to put square root of 2 first. I'm going to put the 1 second, or I should say it's the, I'm going to flip the signs. So I could have also wrote it as negative 1 plus the square root of 2. So you're actually just flipping the signs within the absolute value bars, not just the terms. So because this is evaluated as less than 0, I'm going to flip the signs on my numbers when I write them. So both these solutions of square root 2 subtract 1 or negative 1 plus the square root of 2, both of these would be correct. Let me give you a couple more examples just to make sure that we are okay with that. So again, if you have a complex expression as your absolute value, which is this one here, pi minus 3, the first step that you want to do is evaluate that on a calculator. So pi is approximately equal to 3.14. Now you may have pi on your scientific calculator, but if you don't, you can just put in 3.14. And this time I'm going to be subtracting 3. And that gives me an answer of 0.14. Now 0.14 is greater than 0. And because it's greater than 0, I can just remove the absolute value bars and leave my terms as is without flipping the signs. So the absolute value of pi minus 3 is going to be pi minus 3. I didn't have to flip any of the bars. Here's another example. when you don't have to flip the signs, it doesn't really show you exactly how it works. But so far we see that if our number inside the bars is less than 0, we have to flip the signs. If our number inside the bars is greater than 0, then we keep the answer the same. Try this one. 2 subtract pi. Calculate inside the absolute value bars first. Is 2 minus pi, is it going to be less than or greater than 0? Jacob, Tiffany, what do you think? If you put 2 subtract 3.14 into your calculators, it's going to be approximately equal to negative 1.14. That is definitely less than 0. So 2 subtract pi is going to be a number that's less than 0. Therefore, the answer to the absolute value of 2 subtract pi is going to be, we're going to flip the signs. 2 was positive, so now it's going to be negative 2. Pi was negative, so now we're going to put it as positive. So you can write it as negative 2 plus pi, or plus pi subtract 2. Both of these expressions are the same because the signs are the same on our pi and also on our number. So that's how you do evaluating absolute value when your numbers inside of the absolute value bars are not as straightforward as just a regular integer. So we have some expressions here with radicals, we have some expressions here with symbols, but as long as you calculate inside the absolute value bars first, decide if the number is greater than or less than 0, that will help you figure out your absolute value. If the number is greater than 0, then you don't change any of the signs and you just leave it as is. But if the number is less than 0, you want to change the signs on each of the numbers. Okay, and that's it. That's it for P.1. We went from how we can categorize numbers into real numbers and imaginary numbers and all the subgroups underneath, and then we moved on to looking at identifying sets of numbers on graphs and showing it in interval notation and set builder notation. Then we looked at unions and intersections of sets and how to show that properly, and then lastly we ended with a little bit on absolute value. Jacob, Tiffany, do you have